Okay, shall we start with the book? Should I share my screen or Mayan, could you do that?
Yeah, please do.
Okay, let me. Uh, okay, so last time we stopped, I believe, here, the real-time dynamic programming section, or rather in the end of this previous one. And yeah, honestly, I've moved on with reading the book further, so it's a bit uh, kind of blurry for me right now. But we have a really important topic here to discuss: the uh, like rollout strategies, Monte Carlo research, and stuff. But first, I wanted to revisit this problem, and I've posted my like doubts on Slack. I don't know if anyone looked into it, but yeah, I will still share my observations briefly. Um, yeah, let me just open the. It will take some time to run this notebook, but yeah. So what I've observed for this particular problem, and we can maybe discuss it briefly here, that actually for this kind of problem formulation, the expected value of starting states should be at least like it should be more than 5 because uh, an expected value of uh, maximum of two random variables from standard normal distribution is around well, it's more than zero point 0.5, and we have expected length of the episode here at 10 because we have like a probability of terminating of 0.1, and this would result in the geometric distribution or geometrically distributed length of the episode, and this expected value uh, equal to 10. So we will have longer episode, shorter episode, but in expectation we have an episode of length 10. So the expected value of the Monte Carlo uh, like, or not Monte Carlo, but whatever, like in general, the expected value of this Markovian process would be at least uh, uh, 10 times the maximum of two random variables, but hopefully we will our like actual strategy will perform better than simple greedy strategy, and yeah, in my experiments it does. And so this value should be uh, like around 6 something actually. That is my understanding. It might be wrong, so I was wondering if anyone had this kind of doubts here, or does it seem. And yeah, precisely, I believe the error is in the, and I think I've linked it on our Slack, the oh sorry, the code uh, relevant part of the code here. Yeah, let me even open it, and yeah, I hope everyone can read Lisp code fluently, so that won't be any problem, right? Because Lisp is, everyone knows Lisp, right? And so here we have a summation of the reward of the in terminal state multiplied by 1 minus gamma, and gamma over k, where k is branching factor, and we have the expectation over all branches of the reward here. We might have like a branching factor of 3 or 10 or even 1, doesn't matter. And in this case, gamma is a probability of getting will be 0.9, which in this case stands for probability of continuing the episode, right? So we, with probability 1 minus gamma, which is 0.9, we get into the terminal state, and with probability of like gamma, which is 90%, we get into the next state. But what they have here in this full backup function is another multiplication of gamma, and we multiply what is, we can call this Q prime, right? So I hope that makes sense for everyone. So this is an expected state, yeah, like Q function value for the SP, which is S prime. And I believe in the book they say we have undiscounted formulation of a task, and I think we don't need to multiply by this gamma here, because in this case gamma is not a discounting factor but the probability of continuing the episode. Yeah, so that is my understanding, and that is something I found confusing. So okay, and I don't know if it might be still compiling. Oh no, yeah, we have. And when changing the code to like work in a what I think is correct way, I'm getting here this other values for the expected value of the episode, like expected value of a starting state for an episode. And actually the pattern here for like how the uniform and the trajectory sampling results also change a bit. So in the book, we have like this really big gap between a uniform and on-policy sampling. But once I've changed that in the same number of episodes as in the book, for me, the uniform sampling already outperforms the trajectory sampling, and it's more similar to what we had in the smaller experiment with 1,000 states, and here we have 10,000 states. But yeah, still the pattern is similar to what they have in the book. Like the largest state space, we have the kind of smaller this gap is between trajectory and uniform sampling. And also you should notice that here this is much more episodes before we like, so the plots here have a different kind of x-axis. So it's 10 times number of episodes for this problem. But for branching factor of 3, I still have this pattern that the uniform sampling outperforms the trajectory sampling. But yeah, I'm not sure if that's quite correct. Yeah. Okay, so that is my final remarks on this part of on this part of chapter and on these problems here. Okay. Yeah.
Yeah, I feel the same. Even I have implemented that.
Sorry, Mayank, your volume is quite low. Can you increase somehow?
Uh, is it increased now?
Oh yeah, it's a bit better.
Okay. So yeah, I tried using that and it's still kind of like uh, I came across the same results as you have. So let me try to share my screen, the plots that I had.
Okay, I have stopped sharing.
Yeah. Yeah. So this was the plot that I came with instead of this. So as you can see, there are some issues with this uh, branching factor 1 and on Paul policy 2. There are some issues with this too. And the branching factor 3, of course, there is some issues with this too. As you can see, the red lines, uh, the red and the green, it's like going wayward with the uniform and on Paul policy stuff. So, yep, as you can see here. So, yeah, this
Yeah, it
this is
seems like in this case, the algorithm is failing on branching factor higher than 1. And yeah, I did not observe this kind of behavior. For me, it converged fine. But yeah, I see that here the numbers, like the expected value of a state, are what I have as well, like about 6 rather than something around 3 as they have in the book. So yeah, that confirms it in a way. And
yeah.
also the results for larger the experiment with 10,000 steps, also like the uniform in the end performs better, right?
Yep, yep. True.
Okay, nice.
For the branching factor, uh, this guy here, there was a plot. There was a plot. Let me try to. Yeah, this is the plot. So for this guy, the exercise 8.8. Uh, to branching factor 3, we had as it says, tried with the 1 and with the 3. This is the plot that I came across. For the branching factor 3 uniform and on policy. In this case, it's performing fine. Policy. Yeah, it's the same. In the first part of this state, in the 1,000 parts, this is a Julia code with this guy. They have referenced in the implementation for the 3 repositories to make this function. I'm not too sure what version of the values they had updated with the uniform and the on policy, because I just ran this just before starting up this meeting, so it's still being in the background, as you can see.
Yeah, I believe they also don't have this extra gamma value in front of, you see here that maximum of Q next state. I believe that's the relevant part. And yeah, I think there is a bug in the official Lisp implementation. So yeah, and that's kind of a bit problematic, because for example, in these DeepMind courses, even in the latest one, they are still using the figures from the book. So they do not rerun the experiments. And that's, I don't know, that's not cool in my opinion. Yeah, like, cannot you just, I don't know, make sure that everything works and, just rerun the experiments to show some variation maybe where it exists. And so I think that would be a better practice if there were multiple figures for certain part in the course, rather than like just showing a figure from the book.
Yeah, true. They should have at least replicated and run a bit of variations of them to give a fuller understanding of the various exercises. And they might have also tried some exercises too, while they replicated the figures to give a fuller understanding of the issues that they are that we are facing. So yeah, there are a bit of discrepancies between what the ground truth is versus what the implementation is. So yeah, I feel the same.
When you say the latest DeepMind course, do you mean the David Silver one? From, was it 2015 it was last out?
Oh no, they just released a new version of it. There is a 2021 course, and
is it?
it's
yes.
Yeah. And
is that David Silver as well, or is it somebody else?
No, it's by some other guys from DeepMind. I believe that there is the same guy who taught the course. Like another version of course, I think there is a version for Coursera. Yeah, so but the contents are the same. This time they have 13 lectures, and the like lecture number 8 is relevant to our current chapter. So I watched it today, and they had nice explanations for the Monte Carlo research. We might went through we might go through the slides from this course for it, but still they just from one version of slides to another version of slides, like starting from this the David Silver's course, and they have, I think, like at least 3 versions of it, but still they have the figures from the book, you know.
Right. Yep.
Yep.
And
So
you know, for example,
Hassel.
Yeah. For example, for the other exercises or examples from the beginning of the chapter, yeah, I can just briefly show it if you'd like. But there is a lot of variation in these runs for a maze, at least in my implementation. I'm not sure if that's like, you know, if it's all correct, or maybe I have some issues with it. But you know, yeah, so sometimes I'm getting just the results very similar to what they have in the book. But on other occasions, I can get like substantially different performance of these algorithms. And yeah, just maybe let me briefly show it. What I mean. And yeah, I'm not sure if that's related to my implementation. Maybe there are some constants I might have chosen differently, like number of playing steps and stuff like that. But here you can see the comparison of performance for this blocking maze. So we have a maze with this short path in the beginning, and halfway through the experiment, we change it to be a free path here and block this path here. And you can see there is a comparison of DynaQ and DynaQ Plus, where in DynaQ Plus we have like an additional component in the Q value, which is proportional to the square root of number of time steps since the last visit to the state. So this during planning, and this enforces the algorithm to explore more. And you can see that the DynaQ algorithm in this particular run, it finds a new path much faster compared to DynaQ, right? So the DynaQ run enormous amounts of steps without finding this new path. And that's because during the planning phase, it still has like a low values for this states, and it takes a lot of time to like make sure that we don't have a pass here and update these values here, and then finally, you know, with this epsilon greedy strategy to find this a new pass. And the DynaQ finds it quite quite a bit faster. But actually, I can run it multiple times, and sometimes DynaQ doesn't find it at all, or sometimes it you know, it performs quite well. You know, you see that here it found a new path like in the same amount of time as DynaQ Plus. And in the book, they have a single figure like showing this. Yeah, this nice figure. Okay, this looks cool, right? This enforces your point, but yeah, I'm not sure if that's a true representative of excuse me, a true representative of what happens here. Like, and this is a really simple problem, and yeah, I don't know. On the more complex problems, it might be even more like more variation in the across the runs. Yeah, this other task, it is quite a bit more consistent, but yeah, I guess this one should be here. Yeah. This one is more consistent, but still, you have some variation. Okay, so that's enough with my rant about this kind of not enough of representation. Yeah, I think we should now start with to go further with the book and get into the planning at decision time, because this real-time dynamic programming is actually what we used here for generating this on policy trajectories, right? And yeah, so there is they speak a bit more that some states are irrelevant and there are relevant states, and there might be some irrelevant states, and yeah, but that is essentially the same algorithm as before. And yeah, they've run some experiments on the racetrack environment and got some results here, and also yeah, they also note, you can and they show here that for the dynamic programming, which is like full sweeps for across the state space, they had this number of updates until convergence, and here we comparing with something we run like for 4,000 episodes, but it's not necessarily they converge in the same sense as this does. So they try it until they converge to the close to optimal policy, and that's what this experiment does. And they get this number, which is really not that different from what they do for the on policy dynamic programming, or what they call like real-time dynamic programming, right? But yeah, that's it. We can update either all states with dynamic programming, or all the states we visit. And in that way we can save some compute by not updating the states we don't visit at all. And you see that for this real-time dynamic programming, we have some percentage of states is not updated at all. So because it is not visited by the relevant policies. Yeah. And yeah, I think that's enough of dynamic programming for us, because we are, I was expecting we will be at function approximation part by now, but we had kind of skipped a couple of sessions. Yeah, so I guess let's talk more about planning at decision time. So what we discussed before was this background planning, right? So we do, for each like real world some and planning steps, and we kind of updating our action value function or something using the model, simulated experiences. But here we have another take on planning, which is decision time planning. And this is really very different from the background planning, like conceptually. So we have this heuristic searches where we, yeah, and maybe to discuss it, I think it's nice to look at this slides they provide for this new course. And yeah, so they get to it. Okay, so let's start with this section, planning for action selection. Yeah, and I don't know, maybe Mayank, you want to walk us through it if you're more familiar with Monte Carlo tree search. I think you talked about it before. Or I can do it.
Yeah, please go ahead. We will jump in as and when we have some problems to discuss.
Okay, cool. Yeah, so what do we have? So what is our motivation here? So we want to select the next action and we want to use planning. And I think
I don't think so. We can see your PDF right now. We only have.
Oh, okay. Yeah, let me. I've shared a lot wrong. I think I should share. So can you see now the slides from DeepMind?
Yes.
Okay. So
yes.
Okay, cool. So planning for action selection. Now, yeah, so they speak about the same idea here. So before we were talking about how to improve our value function or action value function or whatever using a planning. And by planning, we mean using the model of the reward process or of our and transitions of our environment to to get the estimates for the future state rewards and state transitions. And now we can try to use this same idea of planning. I mean getting the next rewards and states from a model to improve our action selection. And so they say that the distribution of states that may be encountered from now can differ from the distribution of states encountered from a starting state, right? So yeah, and we can kind of try to improve our local value function instead of improving global value function. We can try to make the action values for our particular current state to make the more informed decision using planning. Okay. And and also our model can be imperfect. And as we briefly mentioned before, so now that we are using a model, there are kind of two sources of inconsistency in or errors in our results. So first are coming from potentially non-perfect estimates of the rewards and next states from a model, and another one is from the errors in our like action value or like value function estimation, right? And when we do this decision time planning, we what we get is just an exploration, right, into the different states, differently distributed exploration, rather than a bad updates for the current global value function. Okay, so what we can, so how do we implement that actually? And we can try to select the action from the current state by running multiple, like unrolling our possible trajectories from the current state using the simulation. And we can build this search tree, and we unroll starting from the current state until the termination. And we use a model for that. So that is why we call it planning, because we use a model and instead of actual experiences, right? For that, and we cannot really do that using actual experiences, because in actual in a real environment, once you selected an action, okay, we are done, we are moving to the next state. Here we are simulating possible next states to select an action for a current state. Yeah, and here you can see a problem, potential problem with this approach. So the actual decision tree starting from the current state can be arbitrarily large, and there is like no way for any kind of interesting problems that we can explore all the possible future states and rewards starting from a current state, right? Yeah. For example, imagine some position in kind of mid game of in chess, and yeah, you can have an exponentially large number of possible future states. So we need to somehow limit our search space. Yeah. So but how do we do that? What our model allows us to do, we can sample like a trajectory starting from a current state. We can run a Monte Carlo simulation, and we can sample a trajectory, and yeah. So, and after that, we can apply a model-free reinforcement learning to simulated episodes, right? So model-free reinforcement learning will just find the action value for this action value function for this state based on the Monte Carlo simulations starting from this state. Okay, so we are just we are using this. So here we have a model of the environment, right? And in this case, we are talking about parameterized model of the environment, and we have some simulation policy. So this simulation policy may be different from our, and like, or should be different from our, say, greedy policy. So it should allow for some exploration, so that we can so that we can kind of search this state space. But on the other hand, we want to explore the states that are associated with higher rewards more, so that we use our compute more efficiently, because we obviously when using a planning at decision time, we have some limited compute we can use for enrolling this trajectories. We cannot do this arbitrarily long, because we need to have some real-time decision making running. Okay. Yeah, and so we do the Monte Carlo evaluation of the observations using the generated trajectories using this simulation policy. Yeah, and then we can use the Monte Carlo evaluation to learn local state value state action function, or state action value function, or sorry, action value function, and then we can take the action in real world by selecting the most useful, like the best action, judging by this newly learned Q value associated with the simulated experiences produced by this simulated experiences. So hopefully this makes sense, and yeah, probably you can have some intuition about why this is a good idea, right? So we can kind of improve our action value estimates in very like concentrated way, right? So we just focus on the current state, and we try to improve our Q function for this particular state to make that decision in this state. Okay, and now we can go to the Monte Carlo tree search. So this is our algorithm to search this tree structure we had here in an efficient way. So let's go through the details for the algorithms. So we repeat this, and we do this repetition basically for whatever amount of compute we have, right? We want to write as many simulations as we can, but we also might have some restriction on the time we have to run this Monte Carlo tree search, because we are to do some action in a real world, and probably there are some time constraints of how fast we should make this decision. Okay, so what do we do here? So we have these 4 stages. The first is select phase, and until we reach the leaf node of the tree, we pick an actions according to our this Q or action value function, and this will be something called our like rollout policy, right? And then we expand a tree by 1 node. So at each stage, we kind of follow this trajectory, and then we add a node into our tree. So we at each iteration we expand our tree by adding the most promising or unexpanded node to it. Then we do the rollout. So until the termination of episode, we follow some, this would be called the rollout policy, I guess. So we follow some simulation policy. So we proceed until termination, and then we update action values for all state actions pairs in the tree. So we do not update all the state action values encountered during this episode, but we only update those states and actions which are already in our search tree, right? So we have this tree here, which we expand gradually. And what we do here is, you see that this is a Monte Carlo update with this kind of the expected returns estimate for the case state here, right? And we use this our policy based on Q value function to evaluate this expected returns. And yeah, we repeat this in a cycle. And finally, what we want to get from this process is an improved state action or action value function for our current state. So we will finally use this Q to make a decision in our current state to select a particular action, which we will do in the real world, and then we transition to the next state, and we will repeat the same Monte Carlo tree search for the next state. So a thing to notice here that we do not update our global action value estimates during this process by default. So we are just updating our kind of local value action value function, right? And and a thing to notice here is that we have two policies. So the tree policy, which we are trying to improve during the tree search, right? And this policy corresponds to our learned action value function. And we have a rollout policy, which is fixed during the simulation. And we are picking some actions which and the note here that this might be just a random policy. So we just want to pick some actions to get to the end of the episode, right? And once we done enough of these simulations, this will give us hopefully unbiased estimate of the expected value for that particular state action pair. Okay, and here is an example for let's try to kind of understand it, the process by example. So we have a current state, and in the a first step here, we take some action from a current state. So here I think the action is blank. and the state is kind of filled. Okay, and you can see that we follow some yeah, you know, there is some inconsistency in naming. So let's call this rollout policy. So we just, it's kind of fixed policy that we follow for the states that are not in our tree. And we get some value. So say here we get a value 1. So now we say, okay, so here our tree policy. We get this, we took this action here, and now we can include it into our tree. And now we select action here according to our tree policy. And let's say this time our rollout policy lead to the reward of 0. So what happens next? Then we yeah, so here we have like an action value estimate for this state being 1/2, right? So we once we had reward of 1, and once we had reward of 0, so it's 1/2 here. Okay, and now we try different action. And this time we get a reward of 1, and the action value for state, the value for this current state is 2/3, and action values here are like 1 and 0 of 1, right? So we count the number of times we took this action, and we accumulate the rewards. And the same for a state. We count the number of simulation from this state, and we count accumulate the rewards observed during the simulations. And yeah, so, and we gradually grow this tree. So and on the tree we act according to our tree policy, which is kind of takes into account our action value function for this states in the tree, but for the rest of the episode we follow the rollout policy. And here you can see that we because this action has a higher value, we are exploring it more. And that is according to our tree policy, it will be explored more. And we keep adding the states into a tree. So therefore we expand with each simulation, we grow the number of states where we act according to the to our current queue, to the policy based on our action value estimates, but we still keep using the default policy for the rest of episode. Okay, so that is kind of an example of Monte Carlo tree search based on some simple simulation here. Okay. So the advantages listed here are following, like we have a highly selective best first search kind of. So we are expanding this more promising branches more compared to less promising ones, right? Yeah. So we evaluate this states dynamically, unlike in dynamic programming, I guess. Yeah. Oh yeah. So to break the curse of dimensionality, we use sampling, which means, yeah, so our the curse of dimensionality, I think occasionally it means different things, but in this case, our tree grows exponentially, right? We like as we proceed with the simulation, our tree can become larger and larger with as we go like further in the tree, and but we can use sampling. Instead of exploring all the possible branches, we just sample random experiences. And yeah, this is parallelizable. This is computationally efficient. So parallelizable in a sense that we can run, multiple Monte Carlo tree searches, and then we can just average all the results for each action. When selecting an action, we can just average the results and for this state, and get the get benefit from all the simulations we run in parallel. Okay, and this is particularly important in a case of function approximation. And yeah, so if you look into all this AlphaGo, AlphaZero, and MuZero algorithms, they combine Monte Carlo tree search and function approximation using deep neural networks to produce like really great results on different games, and yeah, so in different highly complex environments. And they managed to get really strong results without much prior knowledge about any games they play. So that's really, really cool. And the Monte Carlo tree search is one of the core elements of their algorithm. Yeah, and function approximation is another. Okay. Now maybe let's get back to the book. I think that this slides they provided kind of a better explanation into like how everything works there, because there we had like this step-by-step unrolling of this tree, and here we just we observe a single iteration of Monte Carlo tree search. So we start in this state and we have some already expanded tree, right? So, and again, those blank circles are states, I believe, and solid circles are actions, possible actions. And you can see that here we, the blue lines, I guess, yeah, so is our trajectory. And here we, on the tree, we follow this tree policy, which is determined by our action value function. And here with this dashed lines, we follow the rollout policy until we reach some terminal state. And then we just back up the values and we update the action value function for the tree. And yeah, not for the part which is not on the tree, you can see here. So we just back up right from the when we get this when we terminate it, we like update the action value function for the states on the tree, but not outside the tree. Okay, cool. And so here they briefly mentioned that we can, where is the start of the, so the tree policy should be some policy that balances exploration and exploitation. And that makes sense, right? So once we get some reward, we want to explore more, as we discussed before. We want to explore more the more promising actions and states here, but we also want to do some exploration, because like we don't want to get stuck in some randomly lucky branch here, but we want to do some reasonable amount of exploration. And you can use an epsilon greedy policy as we did before in the book mostly, or we can use UCB policy. And yeah, I think I've linked a paper when the authors explain it in a bit more of detail. So these 4 steps, I believe those are a bit more concrete there. So if you'd like, we can go to that relevant part of the paper and just to have a look quickly at the same concept, but explained like in a more concrete way, in my opinion. Okay, so let's again.
Can you link the paper in the chat, please?
The paper is linked in the on a Slack, so that's my message, like last message by me on our channel. And yeah, this is a review paper, and it I think it gives quite like good overview of current like modifications of Monte Carlo tree search, and also they included kind of basics here. Okay, so here again, during the selection phase, we follow the tree policy or selection policy, however you call it. And the phase terminates when a leaf node is visited, and the next node is either not represented in the memory yet or is a terminal state. That's what is selection, right? We follow the tree policy on the tree, and we follow it until we get to some leaf node here. It can be a terminal state, but most likely it will be just some state that is currently our last state we included into the tree. And then we do the expansion. So we are adding some, only a single node. We are included in it in a tree, and further we follow the rollout policy. So here we get into the simulation phase, right? Here, the rollout policy, and then we again do the back propagation, which means we update the action value function for this state. So that's again the same concept. And here they provide more details on what the tree policy can be. And here is a particular like rule which is which can be applied, and I think it's most popular. So this is a UCB action selection based on our action value function, and this term is here to balance the exploration and exploitation. And if you remember the chapter where we went through the bandits algorithms, UCB was one of the most like efficient balancing options we had there. And here we balance the exploration and exploitation based on some, like you see, that it is proportional. And here is a number of visits to, or a number of times we visited this state, and it is divided by number of this actions was taken. And we also have this an logarithm here, so that it does not grow arbitrarily, but it is kind of bounded. So we do not care if this value is like really, I think if it's too large, or even or if it's very large, or even even larger, right? So we just have some kind of logarithmic dependency here, and also we have a square root here. So yeah, and I believe we also briefly discussed why is this particular formula here. But also we have some constant factor here, and this constant is, I believe, for example, in the AlphaGo and like other papers by DeepMind, these constants are like a product of some engineering. So they are selected in some particular way to work best for certain environment, I guess, or I don't know, maybe work best for their approach. But still, yeah. So here you can see what, like in the end, what we will get from this Monte Carlo research. We have a root node, and we have like normalized visit counts for each action, and we will use that as our action value to select our next action. To avoid like selecting outliers, we will rather use a normalized visit counts as our action probabilities, I guess. Okay. Yeah, and there are kind of variation of this action selection approaches, and yeah, there are kind of bunch of them, and yeah, I guess it is best to like use start with using whatever worked best before, and after that you can yeah, try other values. Okay, so right, any questions on Monte Carlo research, or maybe comments, some insights, anything that can help us understand it better, or whatever? Okay, so with that we kind of conclude the chapter, and also we can conclude this tabular method section of the book. So let's briefly go through the concepts we encountered here. So planning is a process which requires a model of the environment, and the model can be kind of given to us, or as it happens in most of the like realistic scenarios, the model is learned as a model should be learned. Okay, it can be an distribution model which outputs the expected values and expected rewards and the distribution over future states, or it can be a sample model which can generate the rewards and next states, but we do not have like direct access to the actual distribution of the state rewards and like expectations of the rewards and the distribution of the over the future state. And in many cases, it is easy, like obviously a distribution model is more powerful, but in many cases it is easy to get a sample model, but it is hard to get a good distribution model for a problem. Okay. Now, essentially, how do we, and there are two ways to use planning. And one is this decision time planning, which we discussed just before. And another one is kind of this planning, which we use to update our global action value function, which is not very different from our regular learning, just it is done with a model, right? So the DynaQ was an example of it. Okay, so this is kind of this two ways you can do planning, and an important part of it is that most of the time planning is like amount of planning you can do is limited by the compute you can have like between the steps, right? So you need to take actions in a real world, but you may have some kind of time to plan in between these actions. And you can use the time to do the Monte Carlo research. You can use the time to run the DynaQ. You can like mix both, I guess, in some way. So that is something that is most probably will be restricted by your problem setting, not something you can choose. Okay, and now let's go through the summary of part 1 of the book. So we discussed a lot of tabular methods, and like a lot of concepts were introduced. And yeah, so this figure here is designed to kind of demonstrate the degrees of freedom associated with like possible combinations of the settings you can have. So here we have like increasing depth of update, and here we have increasing width of update, right? And what do we mean by width and depth? So here in the like uppermost left corner, we have a temporal difference learning. And in temporal difference learning, we like look ahead only one step forward, right? So the update is here, you can see we have state, action, and the next state. And we consider only one action here, right? And if we increase the width of update, we get on the extremum into dynamic programming, which takes So in dynamic programming, we also look into like one state ahead, but instead of using particular action and particular next state, we like do the expected update. So we take an expectation over all actions and all possible future states. So that is our kind of maximal width of an update, right? And now let's look what is maximum length. So the maximum length with a minimal width gives us a Monte Carlo update, right? And in this case, we update, so we take into account the results from the task like unrolled until the termination, but we only we apply the update only based on the particular states and actions and associated rewards observed during a single process, right? So we don't have any expected updates here. We only use a sample of the rewards observed during single simulation. And the like on the maximum here in terms of width and depth, we have an exhaustive search, which is obviously will always give us a best solution, but or perfect solution if we can have it. But obviously, it in kind of most of the time it's prohibitively costly, have prohibitively high cost in terms of compute. So we cannot kind of do it for any kind of large state space and like and when we have any large problem, right? And you can think, imagine some of the algorithms we've learned to be somewhere in between here. Like, for example, yeah, let's talk about something like n-step expected sarsa, right? So it will be in terms of depth somewhere in between of like TD learning and Monte Carlo, and it will use kind of the sample updates for most of the state action pairs, but it will use also the expected update for the like last nth state. So you can imagine it being somewhere like in the middle of this diagram. Okay. And yeah, so we have here, yeah, let's go through this like summary of different dimensions we can have for a problem formulation, right? So we can the problem formulation can be different in terms of definition of return, and it can be like episodic or continuing, discounted or undiscounted, right? And some combinations make sense, and some combination doesn't quite work together. For example, you probably cannot have like undiscounted continuing task, right? Or you cannot efficiently learn in undiscounted continuing task because you don't have this like update, right? So also your state like value function can be action value function, state value function, after state value function. So you can represent your value function in a different way, and this depends on the problem setting. And if you remember, we considered some cases where the after state is most convenient formulation, and in many other cases the action value is most useful for us. And like the benefit of action values is that it is once you have an action value function, it is actually actionable, and but state value value function is not directly actionable. In this case, you need to have some way to like look at what your next states would be if you want to use it for action selections. But for action value function, you can directly select an action based on it. All right. Okay. The action selection and explorations are different ways to enforce exploration. And as you remember, the convergence to optimal policy for many of these learning approaches is only guaranteed when you visit each state like infinite number of times in a limit, right? And a way to make sure that this is true, we should have some exploration. And for example, we can do the exploration in epsilon greedy way. We can use the optimistic value initialization, which will make sure that we visit each state at least once, right? And we can, instead of some greedy sampling, we can use softmax. So we have some distribution over the possible actions to take, and we can sample from a distribution rather than doing this argmax. And yeah, also this UCB update we just looked at, when you kind of select an action based on the how certain are you in the estimate of the action value, and this estimate is done is obtained using how many times we visited this action. Okay, and the updates can be synchronous or asynchronous, which mean we can do the updates in order, or we can just update whatever state we visited right now, right? And we do not have any particular order in which we update the states. And these experiences can be real and simulated. And so we saw that we call the updates based on a real experience learning, and we call the updates based on simulated experience planning. And in a way, those might be very, very similar. So in terms of mechanic, how it works. And so the location of the updates is another dimension. So we can do the exhaustive sweeps, or we can update the values or the state action pairs we actually encounter, right? So and the updates can be done as a part of action selection or can be done afterwards. And I think that means as it like sends us to the Monte Carlo tree search, for example, when the updates are done at action selections or, okay, yeah. And here, how long should, so the memory for the updates is also something that we can kind of vary over in different problem formulations. And yeah, we can select how long the values should be retained. Yeah, and like, for example, in some cases, we can, instead of using a sample mean, we can use an exponentially moving averages. And in that case, the most recent experiences will be like more weighted more in our update, and like less recent experience will eventually be disregarded. So that is, yeah, a lot of like degrees of freedom in this kinds of problems, but yeah, in some situations, many of these are determined by the problem you are facing, and as you saw, that in many cases we couldn't use we couldn't make some of the choices presented here for particular problems, and also some of the choices were obviously better for those problems, and yeah. And yeah, so they mentioned that, of course, these dimensions are neither exhaustive nor mutually exclusive. So we can have any combination of these, and we can have more variants. So, okay, I guess with that we are mostly done with this chapter, and yeah.
True.
So
I think so. We covered everything. The next part is totally about function approximations and stuff.
yeah, we can also try to kind of relate our what we are going through with the lectures of this from DeepMind. So for the next chapter, I guess the lecture 7 will be most relevant, and you can see that these are swapped in the book and in the course, but yeah, you can kind of encounter the concepts in somewhat different order, but still the concepts are relevant. So here we can also watch this lecture for the next chapter, as well as reading the chapter. And this lecture series introduces a bunch of concepts. So they will have like 2 lectures on deep reinforcement learning. We will look through the approximate dynamic programming, and you know, the approximate dynamic programming is a very deep topic in itself. There are like books on specifically on it, but yeah, we will see what we will have in this book about this methods. Okay, so yeah, if anyone has questions or comments, let's discuss now. Yeah, I'm thinking about how do we kind of get more into discussion rather than, someone, like I did today, uh, uh, yeah, like communicating my understanding of the process, because yeah, I believe that yeah, everyone reads the same book, and it might be I don't know, less interesting for you to listen what do I think about it, and might be, I guess, more interesting to tell what do you think about it, and yeah, hopefully we can have a bunch of points to discuss across the book, and yeah.
Yeah, we have the queries, the questions and answers, and I think so. We discuss it every time. The headings and the sections that we try to give voice to each and every member's understanding of what that particular section represents, based on the examples that we try to replicate. So I think so we cover that part too. But yeah, we can always uh, ask more people to communicate their thoughts.
Yeah, yeah, right. And in terms of what, yeah, I've read a bit further in the book, and we will have a bunch of or a couple of like chapters on function approximation, which are like more general in theoretic, and yeah, in that sense very similar to what we had before, but I think towards the end of the part 2 we will be getting to more practical algorithms, so like this eligibility traces mentioned before in the temporal difference learning chapter, and step or I guess and step bootstrapping chapter, and then we will get to the policy gradients methods. So hopefully we will kind of have a look at the yeah, get to the point where we can solve some interesting problems with this algorithms eventually.
Yeah, true.
Okay.
Yeah, I'd agree, and I think it is like it is the best way to like learn how the actual algorithms work is by implementing them. It's just finding the time to do it. So I need to make more of an effort and try and implement them.
Yeah, true. And yeah, on the other hand, I do understand that it might be kind of demotivating to solving these very basic problems like grid worlds and mazes, and it might be kind of more of a practical thing, uh, like once we can use, for example, OpenAI Gym to provide us the environment, and also like then when you can focus on the like implementing the solution exactly one, and when you are given the problem, rather than yeah, like I've did for the previous chapters, when you yeah, like spend a lot of time implementing the environment and making sure that the environment works correctly, and then only you can start with the solution. But yeah, I think the book is like more focused on some theoretical concepts, and like to intended to give us a broad view on the topic, and maybe we can try to speed up through the book and follow it up with some more practical course. For example, I was looking at this course by Levin. If you know, I think he's from Berkeley, and that is a pure reinforcement learning course, but they have their assignments there, and collab notebooks, and yeah, maybe once we are done with the book, we can go to this like a more practical setting, and maybe we can go through the books a bit faster, but then revisit it once we have some questions, and we can go back and try to clear up some concepts, I guess.
Yeah, I have like another book. I think it's by a guy, Maxim Lapin or something. As you say, like it's all dealing with the open AI gym, is it? So yeah, like he sort of like looks at the algorithms, but has like sort of a very practical approach. It's like in PyTorch for it. So yeah, it's good, but I haven't been all the way through it and haven't actually looked at it in a while. But he definitely sort of sets everything up and takes the view that you should sort of write the code to like learn the stuff.
Yeah, maybe you can send a link to it, and we can, explore the options.
The book I have, it's like, I think it's like the first edition of it, and there's like a lot of mistakes. There's like sort of like a lot of printing errors, but I think just the second edition of it's just been released. I suppose it's a lot better. He's sort of fixed a lot of stuff and added like a lot of new things in. So I'll send a link in Slack or whatever to it.
Marco, and can you do the same for the one that you have, that you've seen with the practical from Berkeley?
Yeah, sure. I think I've already posted the link in the.
I'll look for it there. And earlier you said DeepMind combines function approximation with, was it Monte Carlo? You said.
Yeah.
Okay.
So that is like alpha zero, mu zero. They both have a function approximation, and the Monte Carlo research. So you use a function approximation to guide the search to like explore the more relevant states. And yeah, that definitely like the mu zero paper is maybe worth looking at to understand the concepts behind it. And yeah, there are like, Yannick Kilchner's video on mu zero paper, I believe, and as far as I know, he participated in the I think Google Brain effort to re-implementing mu zero, so definitely worth looking at. So if you don't know, Yannick Kilchner is a YouTube guy who explains the paper, but he is not like just a YouTube guy, but actually a researcher, and I don't know. So he is not. Probably wouldn't give you some nonsense for the paper comments on paper. So yeah, I recommend watching his videos. Okay, and yeah, I will look for the link to that course I've mentioned, and I've like briefly started it, but haven't like went to the later parts. So we can maybe do it after we finish the book if there is interest in it. So
Definitely from my side.
okay, cool.
Sounds good.
Yeah.
Yeah.
Yeah, sounds good. Cool.
Yeah, so that's probably all I got. So yeah, see you everyone next time, and I think we should try to go through all of the function approximation chapter during the next session. I know it's quite intense, but on the other hand, the concepts there are quite like basic, and yeah, I think that we should like try to follow this strategy of speeding up through the book to get to more practice faster, and that will kind of boost our learning. Okay.
Thanks, Art.
Cheers. Thanks for that. See you next week.
Thanks, everyone. Yeah.